everyone, and welcome to a discussion on stereochemistry for SN2 and SN1 reactions. I was looking online and didn't see any examples which had line bond for SN2, SN1 stereochemistry, so hopefully this will fill that gap and we'll be able to figure it out a little bit better with line bond form. Alright, so as you recall, we've talked about SN2 reactions before, and we've always talked about something with an electrophile, that's this guy with a leaving group, then we've got a nucleophile, and then that nucleophile is going to react with this to form a product. Now in this case, all that I've done differently is draw a wedge here to show the stereochemistry of the leaving group because it's going to be important. So just remember, if you see a wedge or a dash, that still just means a single bond. It doesn't mean anything fancy, okay? So if I'm looking at these two things and they react, what would be the product of these reagents? Right? It should look something like this. So we should get a product that has the same carbons, right? The 4 carbons here are here. And then on the carbon where the leaving group was, that's where the cyanide's going to go. But what we haven't talked about yet is what is the stereochemistry of that going to be? Is this going to be a wedge or a dashed bond? So what we're going to do is talk about that, and then we're going to come back and add that into this bond, okay? So let's look at it from a slightly different view, and I think that'll be helpful. And we'll also do the mechanism, okay? So let me redraw it in a side view so we can see it a little bit better. So here I have the substrate, the thing with the leaving group here, right? So let's number the carbons so we can map it from here to here, just in case it's not obvious. Also, I want to point out that this is an sp3 carbon because it has 4 things attached. So that's going to be important to the geometry. So I've got my numbers 1, 2, 3, 4, and then here is 1, 2, 3, 4. All right, so the next thing we need to draw is our nucleophile, right? So if I draw my nucleophile, that's going to be the CN. So we'll draw that. Maybe I'll draw it with the N behind it so you can see a little bit better. And that has a negative charge. And then we'll draw the arrows. So we know that the cyanide is going to come and attack the carbon with the bromine. But what we haven't talked about in a little while is that it comes from the backside. So SN2 gives you something called backside attack. So let's talk about why that is. So when you have this reaction happening, it's actually going to attack at a place called a sigma star orbital. So behind the bond between the carbon and the bromine is a sigma star orbital, which looks like this. That's an anti-bonding orbital. So an anti-bonding orbital, first of all, is empty. It doesn't have any electrons in it right now. There's no bonds or lone pairs. So that's a place where electrons can go, and that's why they're going to want to go there. The other thing is that when you have an anti-bonding orbital and you put electrons in it, it actually destabilizes the regular bond. So that's what's going to cause the bond between the carbon and the bromine to break. So it's always going to have to be in the back of wherever the leaving group is. So when we draw our mechanism, we'll draw it from the negative charge at the nucleophile to that carbon. It's actually going to that sigma star orbital. So then once it goes there, that's going to cause the other bond to break. So we'll show that. And it's going to go like this. And then we'll draw what would be the product according to the side view. So let's draw that. So this is what the product would look like. Instead of having the bromine on the right side, now the nucleophile is going to be on the left side. When it happens like that, it goes through a transition state that's actually planar. So let's show the transition state below. So here's the middle part of our molecule, and then we're going to have a dotted line where the bromine is breaking, that bond is breaking, and we're going to have a dotted line where there's a bond forming, right? So it looks like that. So that would be our transition state. And then we would have partial charges. So there's going to be a partial negative over here because it's negative at the beginning. There's going to be a partial negative here because it's negative in the next step. And then that's going to be our transition state. Now note, you don't have to draw this as part of the mechanism because it's not an intermediate. Mechanisms only have things that you can stop in the middle. This is not something that stops in the middle. This sort of just happens. So you don't have to draw this. So now if I'm looking at what happens, it goes here, right? It gets flat, and then it actually sort of flips the other way. So this thing is actually called inversion when this happens. And that's what you always get with an SN2 reaction. And actually you get 100%, like every single reactant is going to work the same way. It's going to invert it. And sometimes they'll describe it as like an inside-out umbrella. So like you go into this part of the umbrella and flip it. So now this side's the inside of the umbrella. But that's kind of hard to see on it without a 3D model. But that's sort of what's happening, okay? So that's sort of what it looks like. So how are we going to translate to what's at the top? So if we're going to draw the mechanism part, we would just draw it with the CN here, right? And it's going to attack the carbon. and then the leaving group leaves. That's the whole mechanism. And then for the product, we're going to add the stereochemistry. So if this is now in the front because we've changed the view, and then we need this to come from the back side, then where would this be? Right, it's going to be on the back because it's backside attack. So we're just going to basically flip it and draw it as a dash instead of a wedge. So if it's a wedge, switch it to a dash. If it's a dash, switch it to a wedge. You're getting inversion. So that product's always going to be 100% inversion, just one product. If you have any questions about that, be sure and let me know, but that's all you have to know for this part, all right? So if there's a dash, switch it. If there's a wedge, switch it, all right? An important thing to notice, though, is one more thing I'll show you. So if we have an example like this where there's just one stereocenter, it's obvious what you're changing. If you had two stereocenters, what would you do? All right, so let's look at this example at the bottom now. So if you look, this has a bromine also, and it's going to be really similar. It's actually wedged, so that's pretty similar. So let's draw what the product would look like without the stereochemistry, and then we'll add it in. So basically the product would look like this if I draw all the carbons and the CN, and then I want to add the stereochemistry. So we said if we have the CN attack at the bromine right here, then that's going to give us inversion. So we would make that as a dash. But if you look on the left side, nothing happened over there, right? So that shouldn't change. So everything on this side is going to stay the same. So we'll draw that as a wedge because it was already a wedge. So just keep it the same. So the only place that something's happening is where the reaction's happening. So just make sure that's what you do. So with that, we're going to pause this video and continue on the next video, but I do want to also talk about the stereochemistry of SN1. So if we are covering that in class, make sure you check out the next video. It's going to look like this. So if you see the reaction, it's going to start like this. This is going to be an SN1 reaction, and then we're going to figure out what the stereochemistry does and how it's different from SN1. So stay tuned for that.